All right, good morning, everyone. So, pardon me, yesterday we started talking a little bit about sound waves. So again, what we're going to do now is we're going to apply all the things that we just learned about with waves and apply it specifically to sound waves. Okay? But at the end of the semester, after exam number 4, we'll come back and we'll reapply all the stuff to light waves, right? Electromagnetic radiation. So basically, even though we're going to abandon this for a little while, it's going to come back to haunt you at some stage. So we can't completely forget about it. At least I'll try to remind you about that when we get back there. So again, we start talking about sound waves. So as we know, a sound wave is a longitudinal wave, which has to move through some sort of medium. So most of the time when we think about sound, we think about the sound moving in air. That's how you hear me right now, but it doesn't have to move specifically in air. It can move within any type of medium. So again, it could be steel, some sort of metal, it could be water, it could be wood, brick. Each one of these will have a different speed of sound. So for example, the way that the sound works is it travels faster in a medium which has more elasticity to it. So the more elastic that it is, the faster that the speed of sound will move. So for example, within inside of this table or within inside of metal, speed of sound will be much faster than what it is in air. Air isn't that elastic, but it's close enough, right? Which is why, for example, if you're walking next to a train or you're walking down train tracks, the best way to find out if the train is coming is actually listen to the train track itself, not listen to air, because the speed of sound travels much faster in the train track than it does in air. Gives you much more early warning than it would be to hear it in air. But in air, which we're going to concentrate most of the time on, turns out that the temperature, speed of sound in air is temperature dependent. So at STP, the speed of sound is typically about 331 meters per second times the square root of the temperature in degrees Celsius plus 273 divided by 273. 273 is here just to make sure it puts into Kelvin. Now, as we briefly talked about yesterday, turns out that the speed of sound we can describe one of two ways. So either we can describe it as the displacement. So in this case, it's going to be the displacement of the air molecules away from their original equilibrium position. Or we can describe it in terms of pressure variations on top of the pressure that is the average pressure in some sort of area. So again, for example, before I was talking in here, we had an average pressure in this room, but as I'm talking, the pressure is going up and down. And in that case, you could describe it as pressure variations on top of the average pressure. Those two things turns out to be 90 degrees out of phase from each other. So when I have zero displacement, I have maximum pressure. And when I have zero displacement, I have minimum pressure, right? Which basically means that when I have zero displacement, I then have the greatest amount of pressure deviation, and so on. So these two things are basically just out of phase from each other by 90 degrees. So if one is described as a sine curve, then the other one's going to be described as a cosine curve. But again, what's the same is the angular frequency is the same. Air molecules are still vibrating with harmonic oscillation with the same angular frequency. The wave number is still the same as well. So the only thing that's different is one's a sine curve, one's a cosine curve. And of course, the amplitude is going to be a little bit different, but they're actually related to each other. So good. We'll just get back in. So now typically, when you hear something, the intensity of the wave falls off as we move further and further away from it. So it turns out that the intensity of a sound wave is proportional to the amplitude squared. So basically what happens is as you move away from a sound, or at least a source of sound, the intensity that we hear gets smaller and smaller and smaller as you move away from that source. And the reason for that is, let's say if I have an isotropic source, so this is what we call isotropic source, which basically just means that it puts out sound in all directions equally. What happens is this sound source, such as me, is creating spherical sound waves. So what happens is, as this thing is creating sound at some sort of frequency, it creates a spherical sound wave. This spherical sound wave then moves away at the speed of sound. So this is going to be the speed of sound, so v of air in this case. Meaning that as it gets further and further away, the sphere gets bigger and bigger and bigger. So at every different location, this is going to have a much, much bigger sphere. Now, even though I'm drawing circles here, what I mean is this is spherical. It's actually a three-dimensional sphere. So the reason that we hear less and less amount of the sound is because as we move further and further away, we encounter a smaller fraction of the size of the sphere. Which basically means that if I was standing here versus if I was standing here, the area which I'm looking at in this area here, so basically meaning that if I was looking at here, the area in which I encounter from the sphere here is much greater portion than what I would encounter at this stage here. So meaning that the amount of the wave that I encounter at this point is much less than what I encounter at this point, which means the intensity is much smaller at this point because I have a much smaller amplitude at this stage. So it turns out that the intensity that we encounter at any portion is equal to P, where P is the power, divided by A, where A in this case is equal to the surface area of the encounter, which is the surface area. So P here is simply equal to the power. And then SA here is equal to the surface area. Turns out that for an isotropic source, the power here is always equal to a constant. So the amount of power which is contained inside of this sphere here versus this sphere here versus this sphere here is strictly equal to a constant. Remember, power is the energy per unit time. So the amount of energy carried by this sphere versus this sphere versus this sphere is exactly the same. But what's different is the amount of area which I'm encountering here versus what I'm encountering here. Anybody remember what the surface area of a sphere is? Remember the surface area of a sphere? Almost, that's a volume. So 4/3 pi r cubed is the volume. What's the derivative of that? 4 pi r squared. Good. So that's the surface area. So we know the surface area here is simply equal to 4 pi r squared. So for an isotropic source, the intensity that we encounter at any given point then is equal to the power divided by 4 pi r squared. So why is this important? Well, this is important because what we perceive as sound level, so what it is that we hear, how loud a soundness is, so basically loudness, is roughly proportional to the logarithm of the intensity. Okay? So at any point, what you hear me, how loud you hear me, or what you perceive as how loud you hear me, goes roughly as the logarithm of the intensity. So the further and further away from me, the less loud you hear me because my sound basically is going to dissipate. Okay? So what we call decibels, which is also known as the sound level intensity, is given by beta is equal to 10 decibels times the log base 10 of the intensity divided by some reference intensity. I0. So I0 here is what's known as the threshold of hearing. Which is equal to 10 to the minus 12 watts per meter squared. Okay, so remember, intensity here is power per area, so this has units of watts per meter squared. So the threshold of hearing is basically the minimum amount of intensity that you need for a normal person of normal hearing to just register a sound. Right. So this is what we call sound level intensity or decibels. So how loud I hear a source has to do with the intensity, and it is at some particular point, which then is in reference to the sound level intensity. So let's do an example. So let's say that we have the intensity of a sound wave from a jet airplane as it is taking off is 1 times 10 to the 2 watts per meter squared. So it's 100 watts per meter squared at a distance of 5 meters away from the source. Then it says, what is the intensity of the sound wave that reaches the ears of a person standing at a distance of 120 meters away? So let's draw where we're going. So here's my plane. There's my plane. Not too bad. For one of my drawings, that's pretty good. So what it says is that some person standing over here is then what? 5 meters away. So let's call this distance R5, which is equal to 5 meters away. And what they're hearing then is what? Let's go back to the problem. So this says that here they're hearing an intensity of 1 times 10 to the 2 watts per meter squared. So that means here we're hearing an intensity I5 equal to 100, or 1 times 10 to the 2 watts per meter squared. Now it's saying some other person is way out here. They are then a total distance of R, let's call that 120, equal to 120 meters away. And what we want to know here is, what is the intensity at this point? We'll relate this to beta in the next problem. So good. So what I want to know is, again, how much intensity does this person hear? And again, this will be related to the loudness. We'll talk about that in the next problem. So how would I do this problem? So what I know is at 5 meters away, the intensity for this person is 100 watts per meter squared. But I want to know, and for a person that's at 120 meters away, what's the intensity that that person hears? So how would I do this problem? Go ahead, Grant.
You define the power of the first part.
Good. And then what?
So plug it back into another equation with your other R.
Exactly. So it has to be true, as we just said, is that the wave carries the same amount of power at every location. So the energy per unit time. So what that means is, since we know the intensity here, we can then use this distance to find the power. That power then has to be exactly the same power that this person hears. So now we know the distance this person's at, so now we can find that intensity. Good. So as Grant said, what we know is that the intensity at 5 is then equal to the power divided by 4 pi R5 squared. Which means the power then is going to be equal to 4 times pi R5 squared times the intensity at 5. Now what we also know is that the intensity at 120 must be equal to the power divided by 4 pi R120 squared. So now if I take this power and shove it in here, what will happen then is the 4 are going to cancel, the pi's are going to cancel. So this then is going to become what? The intensity at 5 times the ratio of R5 divided by R20 quantity squared. Okay? So plugging my numbers, what I get in this case then is the intensity at this point works out to be 0.174 watts per meter squared. So this is the intensity at 120. Okay? Can you see that, or is that squeezed in the bottom too much? Okay. Let's do another problem. So the next problem then says, 4, 5, that the source of a sound wave has a power of 1 microwatt. Everybody know what micro means? 10 to the minus what? 6, good. So 10 to the minus 6 watts. And it then says that if it is a point source, what is the intensity 3 meters away from the source? And then what is the sound level intensity in beta, or in decibels, at this distance? Good. So let's look at this one. So this one says we have some sort of point source. Here's my source, which has a power equal to 1 times 10 to the minus 6 watts. Then we're going to go some distance r away, where r in this case is equal to 3 meters. And we want to know is what is the intensity at this point, and also what is the sound level intensity. So how loud do I hear this thing next? So what do we know? So we know the intensity is simply going to be equal to the power divided by 4 pi r squared. So it's going to be equal to 1 times 10 to the minus 6 watts divided by 4 pi times 3 meters squared. So look at the numbers. And here we find that the intensity is equal to 8.84 times 10 to the minus 9 watts per meter squared. For beta, we now know beta, the sound level intensity, is then 10 decibels times the logarithm of 10 divided by, or logarithm of 10, of the intensity divided by the threshold of hearing. Okay, so it's going to be 10 decibels times then the log base 10 of 8.84 times 10 to the minus 9 divided by 10 to the minus 12. Plug in our numbers. My phone will actually work. Okay. So this works out to be about 39.5 decibels. So this is the loudness at which we hear it. Is okay? Not too bad. Now, since sound is a wave, what that means is that sound waves can actually interfere with each other. So we want to talk about the interference of waves. In this case, specifically interference of sound waves. So, good person that's going to tell us how this thing actually works is Sheldon Cooper. Okay. So, I'll explain what he's doing here in a second, so let's just kind of watch it.
I have a bone to pick with you.
Hi, Sheldon.
Hi, Stephanie. I'm sorry I'm late, but your companion left us an indecipherable invitation. What invitation? We're going to the movies. What movie? What theater? What time? If you were trying to make it impossible to locate you, you couldn't have done a better job.
Oh, clearly I could have.
It took me nearly 20 minutes to go through the browser history on your computer to see what movie times you looked up. Wait here, I'll find us seats.
Oh, no, we have seats.
Not the right seats.
What is he doing?
Finding the acoustic sweet spot.
Does he always do this?
Sometimes he brings a toy xylophone.
Ho! Ho!
I am really sorry about this.
Oh, it's fine. No, sweet.
My apologies, you've been sitting in it all along. When did you want to slide over one?
No, just sit here.
All right, that's enough of that. So, what is Sheldon doing? So, Sheldon is doing, as Leonard had told us here, he's looking for the acoustic sweet spot. So, what does that mean? So, that means that as you're sitting in this room, I am creating a sound source. That sound source is then going from me and reflecting off of things like the wall, right? So, you have the source coming directly from me. It's also going in this direction, bouncing off the wall, and then reflecting, which means you're going to get interference at different locations due to the reflections of my sound. So here, as I'm speaking, it's going directly from you, but it's also going off the ceiling, it's going off the wall, it's going off the floor, it's going off the table. It is being reflected in all different directions, and eventually all those reflections will meet with the original source where you are. Now, what he's doing here is he's looking for locations where you're getting constructive interference, as we talked about before. Constructive interference means that the two waves are coming in, meeting at the same point in phase, which means the amplitude is doubling, which means you're going to get the greatest amount of intensity. Because as we just said, the intensity is equal to the amplitude squared. So the bigger the amplitude is, the greater the intensity will be, which means the louder he's going to hear it. But if I was a single frequency, which is what he was doing there, what'll happen is if it's a single frequency, you'll get points where you have zero intensity because the two amplitudes will come in, the two waves will be completely out of phase, which means you'll have completely fully destructive interference. So you'll hear nothing. Now, if I had something like music playing, things like that, it's not a single frequency, so it's not exactly zero, maximum amplitude zero, but that's what he's looking for here. So he's looking for locations where you have maximum amount of intensity because you have maximum amount of amplitude because you have completely constructive interference. Now, have you ever been to a place like an amphitheater or places where they do operas, things like that? You'll notice the back of the building is actually rounded. The reason that they do that is to get rid of that. So what happens is with the building is rounded, what happens is the wave will hit, it bounces off, but it bounces off behind the location of the audience. So that way all the locations of the constructive and destructive interference happen behind the audience, so there are no dead spots. So not one person is going to hear something louder than somebody else, it'll all be approximately the same. So a lot of research goes into this, a lot of acoustics go in to make sure that people can actually hear their music appropriately. So this is interference. It turns out that to find the locations of maximum constructive and destructive interference, the only thing we need to know is what is the difference between the path lengths at which these sources travel. So for interference, we're going to look at what's known as path length difference. And I'll show you that in just a second here. So path length difference. So what does that mean? So what that means is if I had two sources, I'm going to ignore reflections here. I'm just going to say that we have two sources. Each one of these sources are giving off exactly the same frequency. What will happen is these guys are going to create spherical waves which are going to travel outward. So this is spherical waves for this guy. This one's going to create his own spherical waves. I'm going to do something like this. Now, where these guys meet and where these guys overlap, these are going to be locations of either constructive or destructive interference, depending on how they actually align with each other. So what that means here is for the red solid line with the blue solid line, everywhere that these guys interfere with each other, this is going to give us maximum constructive interference. Because this is a wave crest, this is also a wave crest. These two are in phase with each other at these points, which means that it has maximum amount of interference. These are going to be locations of constructive interference. Now, if I draw a dotted line, which is the location of out of phase, what it means is that this point here, this point here, this point here, and this point here will all then be locations of destructive interference. Which means if I was at this location, this one, or this one, I would hear nothing. So what path length difference says is that we can find the locations where either the constructive interference or the destructive interference occurs based off of the difference between the distance that this wave had to travel and the distance that this wave has to travel. Okay? This is what's called path length difference. So here, if I say this is source 1, this is source 2, then for this location here, this one traveled a distance of d2, this one traveled a distance of d1. So by looking at the difference between these two distances, or these two paths, I can then determine if it's constructive or destructive interference. So the way this works is we say that the absolute value then of the displacement, or the difference between those two distances, which is then equal to the absolute value of d2 minus d1. If this is equal to an integer number multiplied by the wavelength, this is equal to constructive interference. If it's equal to a half integer of the wavelength, this then is equal to destructive interference. Now, technically, this is only true when the two sources are in phase with each other. So when my two sources are in phase, if they meet at a location where the difference between the two paths is an integer multiple of the wavelength, then it's constructive interference. If it's a half integer multiple of the wavelength, then it's destructive interference. Where here m is an integer. So this is 1, 2, 3, actually 0 as well, blah, blah, blah. So this means this is in the integers. This is only true when they're in phase. If the two sources are originally out of phase with each other, these two things switch. The reason for that is, well, so if one wave comes in like this, but the other wave comes in like this, so that these two are out of phase with each other by exactly one wavelength, well, the way that they line up is still they're completely in phase with each other. So this one has traveled a distance where it has traveled the distance further by an amount of the wavelength. This one has traveled a distance, but it's shorter by an amount of the wavelength. These two waves are still in phase with each other, which means they're still at maximums and they're still at minimums at the same locations, which means that they're going to sum together to give me constructive interference. However, if my second wave comes in, and this thing actually did something more like this, where they're now out of phase from each other by half a wavelength, what happens then is they're overlapping where this one is maximum, this one is minimum, this one's minimum, this one's maximum, so they're out of phase with each other, so they can add up to be destructively interfering with each other. Okay. Again, this is only true when they're in phase with each other. They're a little bit out of phase with each other, that just means those two things again switch. Now this thing will only tell you where they occur for maximum constructive and for maximum destructive interference. Won't tell you anything about any place in between. So let's use that and let's do an example. So example says 6. We have two speakers, both with a frequency of 171.5 hertz, are in phase with each other and are separated by a distance of 4 meters. Now we're going to put one of you guys, a student, 1.5 meters away from the left speaker, and what we want to know is at this point, does our students hear constructive or destructive interference? And here we're going to take that the speed of sound in air is 343 meters per second. So let's draw our scenario. So here's speaker number 1. Here's speaker number 2. And we know these guys are separated by each other a distance of 4 meters. Each one of these guys has a frequency. That frequency is 171.5 hertz. Now we're going to put one of you guys here, a distance of 1.5 meters away from the left speaker. And what I want to know is, at this point, are you going to hear constructive or destructive interference? Which one will you hear? So, what do you think? How would we do this problem? How would we do this problem? Based off the things we just talked about. So let's start off with the path length difference. So let's define this distance here as d2. This distance then is going to be d1. So good. So we know that the absolute value of the difference between the two, our path length difference, is going to be d2 minus d1, which is then going to be equal to, well, this is 1.5, and this distance here is what? 2.5. So it's going to be 2.5 minus 1.5 meters. So that's equal to simply a meter. So we know the difference in the path is then equal to 1 meter. Good. Keep going, Derek. What else? Good. So we know that this has to be either equal to m times lambda or m plus a half times lambda. Okay. Now in this case, do we know what m is? No, but what are we looking for? Effectively, we're looking for m, because we know lambda, because lambda is simply going to be what? The speed of sound in air divided by the frequency. So we know that lambda, because we know the speed of sound must be equal to the wavelength times the frequency, so we know the wavelength must be equal to the speed of sound divided by the frequency. We know this part. So, what that means then is we set this, as Derek said, equal then to m times lambda or m plus a half times lambda, which basically means if we take this distance, divide by lambda, that's going to give us a number. If that number is an integer, what that means then is we have to hear constructive interference. If that number is a half integer, then we have to hear destructive interference. So effectively what we're trying to find is this thing a whole integer or is it a half integer? That's going to tell us what type of interference that we have. Good. So let's do that. So we now know we have what, 1 meter must then be equal to some number, I'm going to call that n, times the wavelength, where the wavelength then is going to be what, 343 divided by 171.5, which is then equal to n times 2. So here, that's also meters. Put that in meters. So here the 2 meters are going to cancel. So this means that n then is equal to 1/2. So since n is equal to 1/2, that's a half integer. So does that mean that we're hearing constructive or destructive interference? Destructive. This means we're hearing destructive interference. So this one has to be destructive interference. So that's a good teacher. He doesn't blow out his students' eardrums. Right? Let's do another one. This one's a little more complicated. So this says we have 2 identical loudspeakers are located on the y-axis, where one is at the origin, the other one is 2 meters above it on the y-axis. And it says the loudspeakers are driven by the same amplifier and produce sound waves with a frequency of 784 hertz. Okay? And they're going to be in phase with each other. Let's take the speed of sound in air to be 344 meters per second in this case. So now what we're going to do is we're going to move a microphone along the x-axis, and we're going to look for the locations of constructive and destructive interference along the x-axis. So what we want to know then is what locations will we have destructive interference and what locations will we have constructive interference all along the x-axis. So let's draw our picture. So again, we have, here's our y-axis. So here's our x-axis. So we have one speaker here at the origin, so speaker number 1. Another speaker here, speaker 2. We're told this distance here is then 2 meters away. So now what we know is we're going to take a microphone. Here's my microphone. A little bit like ice cream, but there we go. There's my microphone. And I want to move it along the x-axis here, and I want to know all the locations of the constructive and destructive interference. This is what we want to know. So good. So here, let's define that we're looking at this point. So let's just call this our points that we're looking at. So let's take this distance here to be the distance x away from the origin, which in this case happens to also be d1. So the distance x is simply the same distance as d1. This distance here then is going to be our other distance of d2. So d2, according to our picture, is if we call the 2 meters simply equal to y, then Pythagoras' theorem says that d2 is going to be equal to y squared plus x squared square root. It's going to be equal to the square root of x squared plus y squared. So this means that our path length distance, delta d, is going to be equal to the square root of x squared minus y squared minus x. Okay, this is our path length difference. Now, what we know is what? For constructive interference, this has to be equal to m times lambda. For destructive interference, this has to be equal to m plus 1/2 times lambda. So this is going to be for constructive, and this is going to be for destructive. So basically, what we have to do then is solve this algebraic expression for then x. That's it. Now, I'm going to cheat a little bit. And what I'm going to say is I'm going to let n equal both m and m plus 1/2. So basically, all I'm going to do is I'm going to rewrite both of these two things simultaneously as an n and solve both of these two at the same time. And then I'm going to go back to when I'm looking for destructive interference, I'm going to rewrite n as m plus 1/2. And then when I'm looking for constructive interference, I'm going to write n as n. Basically, I'm just going to be lazy. I don't want to solve this multiple times. What's up, Corey?
Where did you get the x squared minus y squared? Should it be plus?
Oh, yeah, sorry. Thank you, Corey. Everybody's okay? So all I'm going to do is I'm going to rewrite this as x squared plus y squared minus x is equal to n times lambda. So let's just solve that. And then again, when I want to know when it's destructive, I'm going to turn n into n plus a half. When I want to know it's constructive, I'm going to turn n equal to n. That's basically it. So if I want to solve this for x, first thing I want to do is what? If I try to square both sides, that won't help me at this stage, because if I square both sides, I'm going to have a cross term, which is the square root. So first thing I'm going to do is actually add this term to the side. Isolate the square root. I'm going to get a square root of x squared plus y squared is then equal to n times lambda plus x. Now I'm going to go ahead and square both sides. So now if I square both sides, left-hand side is going to become x squared plus y squared. That's then going to be equal to n squared lambda squared plus 2n lambda x plus x squared. Actually, we're going to get x. Always okay? Now, nice thing about this is the x squared terms are actually going to cancel because they're the same on both sides, which means I only have one term which depends on on x, which is this term. So let's isolate this term. So to do that, I'm going to simply subtract this term to this side. I'm going to get a y squared minus n squared lambda squared, then is equal to 2n lambda times x. Or finally, we get x then is equal to y squared minus n squared lambda squared divided by 2n lambda. So this is the expression that we want to solve. Is okay? So good. So all that means then is what? For part A, since we're looking for when we have destructive interference, we're simply going to let n equal to m plus a half. That's it. So I'm going to plug that back into this expression here with the fact that n is equal to m plus a half. So let's do that. So that means I want to solve y squared minus m plus a half squared times lambda squared divided by 2 m plus a half times lambda is equal to x. So here, we're just going to start off with what? M is equal to 0. Plug in m is equal to 0, calculate, solve. So basically, I'm going to choose all my different m's until I eventually run into a negative x value. Okay? And I'm eventually going to run into a negative x value because this term is constant. This term is going to keep growing because m is going to keep growing. So eventually this term will become bigger than this term, which means it's eventually going to become negative. Now we're going to isolate our fact to we're only moving in the positive x direction. So when it becomes negative, we're going to say, I'm not going to worry about it anymore. So if I do that, what I find is, so the first one I find is at the location of, so m is equal to 0, this is x 1/2, which is then equal to 9.01 meters. M is equal to 1, that's x 3/2, that's then at the location of 2.71 meters. M is equal to 2, that's then x 5/2, that's at the location of 1.27 meters. M is equal to 3, that's then x 7/2, that's at the location of 0.53 meters. And finally, m is equal to 4, that's x 9/2, which is at 0.026 meters. So these are all the locations of destructive interference along this axis, on the positive x-axis. Is okay? Okay. So, part B then says, where are the constructive interference? So here we're going to take m is equal to n for constructive interference, which means we have y squared minus n squared times lambda squared divided by 2m lambda is equal to x. So again, we're going to do the same thing. We start off with m is equal to 0. M is equal to 0 corresponds to x0, which in this case is going to be infinity. It's infinity because I'm dividing by 0, and I divide by 0, 1 over 0 is simply equal to infinity. We'll talk about what this means in a second. M is equal to 1. X1 then is equal to 4.34 meters. M is equal to 2. We have X2 then is equal to 1.84 meters. M is equal to 3. X3 then is equal to 0.86 meters. And then finally, M is equal to 4. X4 then is equal to 0.26 meters. So these are all the locations of the positives. Okay? So let's take these answers and kind of see what's happening. So basically what this thing says is what? If my two speakers were here, the first location of constructive interference is way over out here at infinity. So why does infinity make sense in this case? So why do I know it has to be infinity for these things to have the first constructive interference? So why does this actually make sense? So the first thing we want to know is why do these things make sense? So let's go back to our picture. Okay? So what the picture says is that D1 is this distance, D2 is this distance here. So what this thing is saying is what? For these two to meet completely in phase with each other, which means that the two paths have to be exactly the same length. To do that, I have to go an infinite distance away. So what that means is that the length of D1 has to equal the length of D2, and that only occurs if I go an infinite distance away. That makes sense because speaker 2 is already a distance of 2 meters away. The only way to get these two to equal the same length, the same distance at which they go away, is if these two lines become parallel lines. That's it. The only way to make these two parallel lines is if I go an infinite distance away. That's what this thing says. Okay. So again, all this thing says, first off, is the first location I have of constructive interference is way out here. Now, if I start out here at spatial infinity and I start walking in this direction, what'll happen then is the intensity of the sound that I hear will slowly get softer until eventually I reach this position at 9.01 meters away, where I then hear nothing. Now, once I'm here, I start moving in this direction, the sound will slowly get increased because now the intensity is going higher, the amplitude is getting higher, until eventually I run into this location of 4.34 meters, where I now have another maximum. I keep going, the sound level intensity will start really slowly get smaller until eventually we run into this location, 2.71 meters, where I have 0 again. Keep moving, it goes up to a maximum of 1.84, goes back to a minimum of 1.27, goes back to a maximum of 0.86, goes back to a minimum of 0.53, goes back to a maximum of 0.26, back to a minimum of 0.026, and then I'm past the orbit. So what's happening is, so again, if we go back to our picture, we start off way out here with constructive, go to a destructive somewhere about here, go back to a constructive here, go back to a destructive here, go back to a constructive here, go back to a destructive, and etc. These two things are alternating like they should be. But again, for these two to go exactly the same distance, so the path length distance is 0, they have to go an infinite distance away from each other to cause that first location of constructive interference. So these are the locations that we would run into everywhere along this path for constructive interference and destructive interference. They would just completely keep alternating with each other. If I kept going in this direction, that would also be true in this direction. They would just completely alternating with each other as well. Okay? Now what's interesting, we'll talk about this soon, this is only true if I move this microphone like this speed. Because if I start actually moving it at a faster rate, what will happen is actually all these locations will move. And the reason all they're going to move is what we'll talk about for the very last part of this section is called the Doppler effect. So what happens actually in the Doppler effect is the frequency is going to shift because of the motion of the microphone, which will actually cause these locations to move. So to find the true locations for these things, we have to move it very slowly so that way we don't change the location, because otherwise we're going to change the frequency. So we have to be careful on actually how we do this. The faster we move it, the more the frequency is going to change, which means the more the locations will change as well. So again, this is a path length difference. I can find the locations where I have constructive and destructive interference by simply knowing the difference between the two paths. If the difference between the two paths is equal to an integer multiple of the wavelength, when they're in phase with each other, that gives me constructive interference. If they're a half integer times the wavelength difference, that's equal to destructive interference when they're in phase. If they start up out of phase, those two things switch. Constructive then becomes half integer, destructive becomes whole integer. So just be careful with the problem. Just know if it says in phase originally or out of phase originally. So tomorrow we'll start talking about standing waves again. So now we'll talk about wind instruments, standing waves with those. We have two different types. There's going to be reeded and unreeded, which corresponds to either two open or one open and one closed endpoints, like what you did in lab. So we'll talk about that tomorrow. So any questions on this? Okay. So path length difference is typically one of my favorite questions to ask on an exam. I'll tell you, there's usually something to do with that on there. Okay, so I'll see everybody tomorrow. Have a good day. Got to bend down my poor broken knees. So, dude, okay? Have any questions or anything?
I'm good for now. Thank you.
All right.